Hello, so in this video, in order to kind of start talking about what's happening with differential equations around singular points, we're going to have to start looking at this thing called an Euler equation. Now in this video, it's just going to be simply an outline of the Euler equation. So if you just want to learn the facts, then watch this video. But I really encourage you actually to look at the next few videos on where the kind of, where these facts come from and kind of the ins and outs of them. Because it's just going to help you with your mathematical vocabulary, as I call it. You get more experience with with kind of where things come from. Then it's obviously going to help you later on down the line, because you've looked at a lot of the methods already. So basically, the Euler equation, if you remember, is something that looks like this. So I always think of an Euler equation is where you've got a quadratic hidden within a differential equation. So you've got a differential equation, so y double dash, maybe if I do this in a different colour actually, so I've got y double dash, second derivative, okay, plus then something involving the first derivative, plus then something involving y, and for the Euler equation it's fine to set this thing equals 0. So this is our differential equation, okay, but the Euler bit comes in because it's a quadratic hidden within this. So the quadratic, we've got x squared plus some constant times x, plus just some constant on the end, okay? And this is what's known as an Euler equation. And we give this, this is actually a linear operator. If I've talked about what a linear operator is before, it's basically a function, yeah? But instead of it being, we can't call it a function because with a function, you put a value in and you get a value out, okay? Here, you're putting a function in and you're getting a function out, so therefore we call it an operator, okay? And it's an operator which involves the function y. Okay, because that's obviously where the derivatives come in. That's the differential part. So, yeah, this is basically what an Euler equation is. It's a quadratic hidden within a second order differential equation. All right. Now, the solution of an Euler equation is typical of all ODEs with regular singular points, which is why we want to examine this. Okay. And basically, the way in which we solve this equation, okay, and again, I'm going to talk about where the solutions and things come from, it basically comes from the fact that when you we look for a solution of y equals x to the power of r, that's the solution which we're after, okay, and it comes from solving this thing here, so it comes from solving this thing over here, so it's r squared plus alpha minus 1 times r plus beta, okay, which basically simplifies down to r minus r1 times r minus r2. So these are the two roots that we're looking at, r1 and r2. Like I say, I'm just giving you the raw basic facts here. But again, I'm going to show you where they come from in the next video, so don't ever go at me for not showing where they come from. All right. So basically, you solve this thing here, and this will tell you what R1 and R2 is. Okay, and then you've got three different cases because obviously you've got a quadratic going on. So you've got three cases. You've got the case where R1 is equal to R2. Okay, and that yields a solution that looks like this. So the general solution looks like this. So it's you've got C1 x to the power of R1 plus C2 x to the power of R2. Okay, then the next case you've got is when R1 is not equal to R2. So this is case 1, this is case 2, when R1 is not equal to R2, and that basically yields, sorry, no, that's the wrong way round. So when R1 is not equal to R2, you get this, okay? But then when R1 is equal to R2, so in other words, you get equal roots next, then you get something this form. Sorry, I wasn't quite concentrating there. So when R1 is equal to R2, so in other words, you get the same roots from this quadratic equation, then basically you get this, so you get C1 x to the power of R1, okay, plus C2, and then to differentiate the two things, because of course you have to have two solutions. To differentiate the two, with the whereas before we've seen it as e to the power of RT. Here we need to differentiate the two, and normally we stick an x in front of it. We can't stick an x in front of it because we're already using x. So therefore we're going to have to use a natural logarithm of x to differentiate the two, so it'll distinguish the two times R1. Okay, and then the third case, like I say, I'm going to go through all these in detail and derive them all for you, is when R1 and R2 are complex. So in other words, we end up with complex solutions, okay? And that yields a solution like this, so it's y equals e to the x, y of x equals C1 times x to the power of lambda, cos mu times ln x, okay, plus C2 x to the power of lambda sine mu times ln x. Okay, so these are the solutions you're looking for, and of course you're looking for R1 and R2. So R1 is equal to lambda plus mu I, and R2 is equal to lambda minus mu I. Okay, so these are solutions that you're looking for, basically. And we're going to talk about where these things come from. But basically, if you just want the raw facts, then here they are.